Hello everyone, this is Mr. King speaking. This is Math 1314 and this is the lecture video I am preparing for section 1.9 on inverses. And so let's begin. I'm going to start from your WebAssign homework assignment. And at the bottom are two problems. I think it's a nice place to begin. So let's do that. So number 21, it says to use the tables. So here's a table of a relation. Well, it says it's a function. So these are some of the points on the function f of x. And thus, for example, -1 is the domain value and 4 is the range value or its mapping. So that would be a point on the graph of f of x, and same with the remaining points. So 0, 6 is a point on f of x, and so forth. And they're asking us, well, if we know these are points on the function f, then what are some points that are on the function f inverse of x? And then they say, order your answers from the smallest x value to the largest x value. So to start out, everyone, inverse, the most basic understanding of inverse in terms of points is to simply invert the x and the y value of a point on its graph, and simply invert the two numbers that are in the ordered pair. So if -1, 4, if -1, 4, and let's just pretend this is 4, that's a point that's on the function f, then the definition of inverse, inverting, switching, inverse, then, so if -1, 4 is on the graph of f, then you switch the point. So instead of -1, 4, it would become 4. So instead of the point -1, 4, which they give us, is a function, is a point on f, or f of x, then, well, the inverse partner point, if you will, is found by simply inverting the two values, the domain and the range value, the x and the y value, around. So inverting or changing, we now have that on the inverse graph, which is f to the -1 of x, then the point for -1 will be on the graph of f inverse. And well, we'll just leave it at that for the moment. So that's what inverses mean. So this is f inverse and f. They are inverses of each other. And so if you know a point on one of the functions, then you will automatically know a point on its inverse, because you would just invert the points, the x and the y value. So, so here we just simply do that. So they want us, we're going to invert each one of these. So this will be the -1, 4 will switch to the to the 4, -1, like we just did over here. And the 0, 6 would switch, invert to 6, 0, and so forth. And they want us to write all these down and start with the smallest. When you switch it, start from smallest to largest. And it looks like they kind of helped us out here because these are also in order. So the first point would just end up being this one, because these are the y values for function f. And so when you invert them, they will become the values right here for x. And 4 is the smallest one, so that's where we'll start. So simply the 4 and the -1. And the 0, 6 inverts to 6 and 0, and so forth. And there would be the corresponding points from these points up here that are on f. Then we would know by the definition of inverse function that these points would have to be on the inverse of f, or we can say f inverse. This notation here represents the inverse of the function, whatever we write here, f. And simple as that. And the same thing down here. So you guys can do that. Just make sure when you write, you're supposed to write the smallest x value first. So if we look here, this y value of 10 is going to become an x value when you invert it. So we're supposed to write the smallest x value that we're going to get from all these points after you invert them. So if we look here, the current y values are here. When you invert them, they're going to become x values. And since this is the smallest number right here of all these y values, then we're going to have to write that one first, according to the directions. There's really no great mathematical reason other than just to write them in order in terms of x values. So you would just do that. And this would be the next smallest x value, and it would map to 0, and so forth. So, well, we already started, so -5 and -1, 0, -2, 5, -3, and 10, -4. And so of all these x values, this one is the smallest, and this is the next smallest, and so forth. So we are going from smallest to largest like they ask us here. Okay, so just double checking, and looks good. And here we are, and we're good. Okay, so that's just the basic idea of an inverse in terms of points. They're just inverted. And now we're going to look at when you do that for a whole graph, so not just for some of the points on a function, but the entire graph. So Okay. So I'd like to show you, oh, let's see here. Okay. So I'm going to go to Desmos, and I have here some functions already put into Desmos here. And this may look a little strange. This is f of x equals, and it's really just x squared. So it would be like this. Y equals, or I should say f of x equals x squared plus a constant. Okay, and I have, that's this part right here. And this is the domain. So the domain is only for x values that are greater or equal to 0, which is starting right here and going forever to the right. So this blue graph, this blue just happens to be blue, it's only going to be x squared plus whatever a value, but starting only at x equal to 0 and then to the right. So so let me turn off this one and this one. So notice here's the blue graph. It's only half. It's only half of the parabola. The other half would be over here. It would go up like this. But since we restricted the domain, then that's why we only have the graph starting at x equal to 0 and also greater than 0. A represents the vertical shift. So right now A is at 0, but if we move it 1 to the, as we move it, you notice the graph is going up. And same if we go negative A values, the half of the graph, it is, well, it's a vertical shift. So now it's down whatever this number is, negative 3.1 or something, or negative 4. So then this graph right now would be x squared plus negative 4, or just x squared minus 4. Okay, and what I wanted to show you all is that, let me go back to the simplest, the most simple case, and that's when a equals 0. So it's just x squared, and it's again only half of that parabola because of the domain restriction. So then I want to turn on the basic parent function of a slanted line, y equals x. So remember, everyone, and then I'm going to put a point, emphasize a point on x squared, the blue graph. So for example, the point 2, comma, if you put 2 into the squaring function, well, 2 squared is 4. So I just wanted to emphasize this point right here is on the original parabola. And if we now, so this function will have an inverse function, and this point on the original function when you invert it, just like on our exercises we just looked at, the 2, 4 inverts to, you invert it, so the 2 and the 4 switches around, and you'll get 4, 2. And the point 4, 2 is clearly right here. And let me pick a different color. Maybe decisions, huh? Let's say orange. Okay, so notice 2, 4 on the original function will invert and become 4, 2. Now that will happen for every single one of these points. Yeah. So for example, 3, 3, 9, three, 9 is on the graph right here. If I were to find it here, there's 3, 9. And so this point will, in the inverse function, this point 3, 9 will have a partner point over here, and it'll be 9, 3, which is right here. So if we do this again, 3, 9 on the original graph, and let me just change this to the same color. So let's say the red, and let's label it. Then when you invert it, that point, which is one part of inverting this whole blue parabola, this half parabola, well then when you invert the point 3, 9, of course, we're going to get 9, 3. And let me change that color as well so that we have the orange still. And label it. So you can see here's 9, 3, here's 3, 9. So for these 2 points, then 2, 4 and 3, 9 on f of x, then the point 9, 3 will have to be on the inverse graph of this f of x graph. So when we graph this equation, it better go through 4, 2 and 9, 3 and so forth. Here's a point, 1, 1. If you put 1 into x squared, remember this is just x squared plus 0 for the moment. I have it at a equals 0 here. So if you put if you put 1 in and square it, you get 1. So that's why 1, 1 1, 1 is on the graph of x squared. And say I put it in red. Well, when you invert 1, 1, well, that's kind of interesting because when you invert, since they're both the same numbers, 1, 1, when you invert them, they're still going to be 1, 1. So that means when we get the graph of the inverse function of f, which remember is f inverse, f to the negative 1 of x, the graph better go through, we could keep doing this, remember, for all kinds of points, for an infinite amount of points. And every one of these points, if we knew what they are exactly, when you would invert them, the x and the y would switch and you would get more and more points along here. And if we then connect them all, we will get the graph of f inverse, and it better go through, it'll have to go through the 1, 1, the 4, 2, the 9, 3, and so forth. And by the way, here's another one, 0, 0. So notice 0, 0 is the very beginning point on the function f of x, the blue graph. And so 0, 0, when you invert it, will still be 0, 0. So there's another point that won't change when you invert it. Now, another interpretation graphically is the point on the first function, if you call it f of x, and its partner point on the inverse function, f inverse. Not only are they inverted, 2, 4 to 4, 2, 3, 9 to 9, 3, and so forth. But if we take a little, if we look here, and I'm going to attempt to draw a line from this point on f to this point on the inverse point. And if we connect a line, and forgive me if I don't draw this very well, and I'm not 100% sure where it goes through, and I just destroyed it. But if we could, if I was able to draw a straight line, yeah, then this segment from this 0.24 to the y equals x line, this distance, if we measured this distance, if you reflect it over at a right angle, so you pick the straightest distance, the closest to this y equals x line, reflect it over and you'll land right on this 0.42. So this distance and this distance are congruent. They're equal to each other, okay? So this point would reflect over to this point. 939, and I'm almost afraid here to try to draw a line that's that goes all the way through here, but I'll give it a try, and it'll look terrible, but oh well. So please use your imagination. That's that's meant to be so if we draw a line segment from 0.39 to this green line, and we draw it so it's perpendicular to the green line, then when you reflect this point over this green line, it'll land right here. Or another way of saying it is this distance from here to here is congruent from here to here. So that's a unique geometric property of when you reflect a point over the line y equals x at a right angle here, you get the inverse point. So if we kept doing that, so just for example, I'm really risking it here because this is just freehand, and just pretend. So it may be, if that distance is the same as that distance, and if I drew a straight line at a right angle, then this point, it would be somewhere around here. And I'm sure I'm off by somewhat. But anyway, if you kept doing this, then this point reflected over the y equals x line would land the same distance on this side, and it would be roughly here, and so forth. And so if you did keep doing that, and by the way, these points over here would reflect over to here. So there would be a point like right here, and so forth. And so by the time you try to connect all those points, this piece will invert and you'll get a reflection, and it'll look something like this. Here they are equal again, because 1, 1 inverted is still 1, 1. And now we keep going. Now, this is just a really bad sketch. Oh boy. And I'm embarrassed here. So, and we'll actually graph it in a minute. And you can see how bad I just did. But it was supposed to go through here. But hopefully you can see this blue graph reflected over this y equals x line will give you a curve this way. And that will be the inverse graph. The inverse, and this one is f, or f of x. F of x and the inverse of x. Now, what would be the equation of the graph that is the inverse right here? What would be this equation? So all we have to do, everyone, to do that is to simply write y equals x squared is this parabola, it's the half of this, it's only half the parabola, remember, but it's still of this, from this equation. And the inverse, if we invert, just like we invert a point, the x and the y gets inverted or switched. When we invert y and x here, or x and y, we get the inverse equation. So when we invert, the x and the y simply switch places, and there would be the inverse equation. Now, if we solve for this new variable y, so that normally you have an equation of y equals, so if we solve for y, this already is the inverse. This is the inverse. I mean, there's a domain issue here, but when we solve for y, now solve for y. And to get rid of a square, we would square root both sides. So if we take the square root, and we would get y equals plus or minus the square root of x. But since x had to be positive to begin with, that was the domain we had, x had to be greater or equal to 0, then when you invert it, y has to be greater or equal to 0. So therefore, y has to be positive, so we're going to ignore this -1, and then we would just get y equals square root of x. So this would be the inverse of f, where f is the x squared. Okay, if we ask the computer Desmos to graph that, we could say y equals the square root of x and there you see the red graph here is the inverse of the blue graph, and you can see how lousy my sketch was here, but hopefully you get the idea. Yeah, so that's one way to get the inverse function, is to take the original equation and simply invert the y and x, because that's what inverse means. Solve for the new y, and sometimes you'll have this domain issue where you'll have to take one of these pieces away, and we had to here, so that y would always be positive. Because here x was always positive, so when you invert it, y will have to be positive as well. Anyway, so another way to graph this is to use this note, is to do this right here. So instead of f of x this is just a Desmos thing here. F of x is equal to the y. If you invert then we would have f of y equal to x. And so this would be the inverse without solving for y. And so if we ask Desmos to if you type x equals f of y, it'll graph this inverse as well. And I'm going to erase this one, or just turn it off, and turn this one on. And there you see, it's just a different color. Let's say I change the color, there's the red, and there you go. It's the same one. So that's another way to get the inverse, is if you type in f of x equals whatever the equation is, x squared, then you can also just type in x equals f of y on Desmos, and that'll give you the inverse as well. Okay, so I'm going to clear all this out. And now, one more thing. If I'm going to erase these points, let me see what happens when I don't. Yeah, I need to erase them. So what if I go back to a equals 0, that's when we had the original function f of x equals x squared, or y equals x squared plus a, but that's when a is 0. What if we shift the equation or change it? Let's say we go x squared plus 1. So this blue graph is the x squared plus 1. And now its inverse is this red one still. That's this part. Here's the reflection line. And so notice this graph reflected over the reflection line gives you the inverse graph. Or another way to think of it is, if you pick any point, here's the first point on the f of x. When you reflect this over the reflection line, y equals x, and when you reflect, go at a perpendicular to this reflection line, and then reflect it the same distance to the other side, then it'll, as long as this is congruent, then this point 0, 1 will reflect right to here, and this will be the inverse point. 0, 1 will become 1, 0, like that. So 0, 1 here, and right here is 1, 0. They are inverse partner points, meaning when you reflect or you invert 0, 1, you get 1, 0. And the same with all these. So this, but any point you pick, you reflect it, and it'll land on its, and when you reflect it, that point that reflection point will be on the inverse function. So here's a simple one to see. 1, 2, if I can show you. 1, 2, when you reflect it, it'll become this point down here, 2, 1. Okay, and so forth. So I hope that makes sense. And you can see if we move the slider now, this just gives us different version. Of course, if we turn this off, then all you're going to see is the original function f changing, and it's just shifting up or backwards down. And when you do that, well, wherever you decide to stop will be a brand new equation. And when you invert it, well, then this graph reflected over this reflection line, y equals x, you'll get the inverse graph. So if this point right here is the very beginning point of f, 0, 4, well, when you invert 0, 4, of course, 4, 0 will be the corresponding partner point, inverse point of 0, 4 will become 4, 0. So as soon as I turn back on this inverse graph, well, then you'll see it starts right here at 4, 0. And then you could keep going. Here's 1, 5. Well, then 5, 1 will be a point on the inverse. So you'll start to get something like this. So turn that back on, and I hope you see there's the 4, 0, there's a 5, 1, and so forth. So you have this relationship between a function and its inverse. Yeah. So it doesn't really matter which one you call the first function. If you want to call, if this one was the one they gave us, and they said graph the inverse, well, then it would be the blue one would be the inverse. So it's not that there has to be, oh, this is the only one that could be the original one. It's just whichever one they give you, the reflection over the y equals x line, or inverting all the points will give you the inverse graph. And then we could get the equation. Yeah. And so what this lesson will be is to practice these ideas. And by the way, look what happens when we move this graph shifted down below. Then this graph, so if we get down to 0, -1, well, then this graph is going to become, this graph will move over here. So that's kind of neat. So this would be right at a equals -1, x squared minus a. I mean, x squared minus 1. And then we're going to be asked how to find this equation right here. Okay? Okay. One more thing, and then we'll be able to look at the homework, and that should be it. I'm going to clear these out and show, well, let's see here. How about I just turn this off? Turn this off. Go back to a equals 0, just because that's fairly simple. Okay. So another thing that we need to talk about is, and it's nothing new actually. So if we pick a point, I'm going to pick the point, oh, how about the point 3? This is 3 right here. Let me change this. Oh, I didn't want that. Okay. So let's take this point 3, 9. So right here somewhere is 3, 9. Okay, and we're gonna, so we know 3, 9 is on the graph because so there's the point 3, 9. And then a moment ago, oh, I'll just type in the inverse. We proved it. I wrote it down. I showed it to you, and it was y equals the square root of x. And here is that, the green one. And so since 3 comma 9 is on the original function, then 9, 3 better be on the inverse function. And so if we type 9, 3, it better be a point on that inverse graph, in which it is. Okay. So nothing new. Okay. Now I do want to show you, this is just, the notation is what I want you to realize. And then, so I'm gonna, so we know that 3, 9, the ordered pair 3, 9, x comma y is on the graph. It's on the function f. So another way to write that is, or if we take f of 3, this 3 right here, put it into the function, which by the way is x squared. F of x equals x squared, remember. X squared, then we get 3 squared. 3 squared, which is 9. So f of 3 is 9. And that's what this is right here. And if we now take the inverse function, and which we, is this one, the square root of x, we did that already. And now if we put in the answer, the domain value from this point, f of this 0.39, this point, if we put the range value, the mapping value, the y value, 9, into the inverse function, so that's like saying the square root right here, and put in the 9, yeah, then we get the square root of 9 is 3, of course, and we get 3. So if you put 3, domain value 3 into the first function, f, we get a mapping of 9, because 3 squared is 9. If you take that mapping value, that range value, 9, and put it into the inverse function, well, you get back to 3, because the square root of 9 is 3, and that means, yeah, so since you put 3 into the function f and you get range value 9, if you put 9 into the inverse, if you get back to 3, which we do, so that means, thus, the point 9, 3 is on f inverse. Now we already knew it was the inverse, but normally we're going to be asked to check it this way. So we knew it was the inverse because we've been exploring here. But what happens is this: if you put any point that's on the original given function, well, let's say they call it f of x. So if you put the domain value into the function and you get 9 as the range value, which means it's a point on the graph of f, and then if you invert the domain and range and put this range value 9 into this other function, and if you get back to 3, well, then that means 9, 3 is on the new graph, which right here it is. Well, then that means that if 3, 9 is on the first graph and 9, 3 is on the second graph, then it may not be proof to do it just with one point, but it certainly is a strong indication that these are inverse functions of each other. Maybe we'd try a couple more points to feel comfortable about it, but that is enough, provided the original function is a one-to-one function. Well, then that'll make then this will be a true statement. But anyway, so another way to write that would be to say, so and I'm going to switch to my notebook here. So I was scribbling here before, and I'll just borrow my scribbling. And I have here, everyone, if f of x is x squared, so then the point 3, 9 is on the graph, like I was showing you. And then let's say they give you another function and they don't tell us it's the inverse. They just say it's g of x, another function. Well, and if we try this, so one way to test, are these two equations inverses of each other, is to say, I'll take a point on the first function they gave us, 3, 9 is a point on this graph of x squared. And if you put 3 into the function f, well, 3 squared is 9, which we know already. Now, if you take this mapping of the first function, 9, and put it into the second function, g, and you plug it in, the square root of 9 does get back to 3. Well, then that's telling us these two equations are going to be inverses of each other. Another way to do what we just did here is to write it like this. So here I wrote f of 3 equals 9, which we know. Put this 9 into the other function, which just happens to be named g. And when you put 9 into the function, the square root of 9 is 3. Another way to write this is to write it like this. In composition form, remember, the first thing we did was put 3 into the function f. And whatever answer we get, put that into g. Another way to do that, these two steps, is to just write it in one step. And it says put 3 into function f, which is this part. We would get 9. And then whatever answer we get, which is 9, put it into g. And if you put 9 into function g, the square root of 9 is 3. And therefore, when you put the main value into the original function, and then whatever the mapping is, 9, put that into the other function, that's what this says right here. If you get back to this original number here, 3, well, then you know these two are inverses of each other. Therefore, f and g are inverses. So, in general, if we have any two functions, say we have two functions, f of x and g of x, and the question is, are they inverses? Are they inverses? Question mark. What we can do is put a specific number in, like we did over here. Put in the point 3, get the mapping 9, put 9 into the other function and see what if we get back to 3 or not. In general, though, we'll say for any x, you put it into one function and we'll get some range value. Range value, say it's r for range value. Now put r, the range value, into the other function. And if we get back the same x value, if this was a number like the 3, and if we get 3 back, well, then we know they're inverses of each other. But in general, we can do it for just any x value and just literally leave the x there. Get the range value as an expression, not as a specific number, and put that expression right here instead of the 9. Instead of this being a 9, it'll just be an algebraic expression in general. Put that algebraic expression and put it into the other function. That's like putting 9 into the other function. And if we get back to 3, like over here, we know they're inverses. Or in general, if you get back not to 3, but back to just the single letter x, then you know they're inverse functions. So a shorter way to write this is like a short way to write this, and that is to say, put f of x into, so you have x goes into f. Here you'll get an algebraic expression instead of the number 9, for example. Put that algebraic expression into the other function g, and that's the same thing I was just saying right here. And if we get back to x, well, then we are feeling pretty good about these two functions being inverses of each other. But actually, we have to show it two ways. Show in two ways. And the other way is just reverse. You first put a number into the g function. Whatever mapping we get, you would then put it into the other function. And if we get back to x again, then if both of these happen, then they are inverses of each other. You have to show f and g are inverses. Then they will ask us to show both of these compositions. Okay. So I'm going to break this up into 2 lessons, and I'm going to stop it now. And then when I come back momentarily, I will begin the exercises. Okay? Okay. Well, thank you very much, and I'll be back for this part 2. Okay. Bye for now.